dear students, welcome you all. So in this lecture, I am going to discuss about the Fermi theory of beta decay. Right? You can see here. So Fermi theory of beta decay was given by Fermi in 1934. Right? We know very well that what is beta decay. So till 1934, we don't have a suitable theory that can explain beta decay. So in 1934, Fermi explained the beta decay while taking into account the Pauli's neutrino hypothesis. We know very well that what is Pauli's neutrino hypothesis, right? If I write down the reactions of beta decay, we know in beta decay we can have three type of reactions: neutron converting into proton plus electron plus anti-neutrino associated with electron. This is the first one. Proton converting into neutron plus positron plus neutrino associated with electron. This is the second reaction. And the third one is electron capture, that is proton plus electron, that will give you neutron plus neutrino associated with electron. So these are the three reactions that are involved in beta decay. So till 1934, we don't have any suitable theory that can account this reaction, this nuclear reaction, right? So the Fermi was the first person who has explained this reaction. So for explaining it, he has took certain assumptions. I am coming to all of them one by one. So the first assumption is that the light particles means electron and neutrino, they are created when there is a transformation of neutron into proton or proton into neutron inside the nucleus. You can see all these reactions that I have written here. So it is spontaneous conversion of neutron into proton or proton into neutron, or vice versa, we can say. Now this is the first assumption, right? In the second assumption, it is assumed that the energy remain conserved. If I take, for example, this particular reaction, the first one, that is beta negative decay, neutron convert into proton plus electron plus anti-neutrino associated, then in this reaction, the energy always remain conserved. I can write this reaction in the form of parent nucleus X that convert into daughter nucleus Y, plus we have an electron and we have this particle. So according to Fermi theory, the energy remain conserved in this nuclear reaction. The available energy of the reaction is shared by the electron and the neutrino particle, whereas the daughter nucleus does not share any energy because its size, mass is very large, so it don't get any required energy or any energy in this reaction. We can say that the maximum energy, that is the energy of this reaction, it is taken by the emitted electron and neutrino. So this was the second assumption, right? Now I am coming to the third one. This assumption is based on Pauli's neutrino hypothesis. We know, according to Pauli, neutrino is a particle that has a zero rest mass, or we can say its rest mass is very small as compared to the mass of electron, and its spin is half integral, right? It moves with very high velocity, we can say with the velocity of light, right? So all these assumptions were there for the properties of neutrino, right? The fourth assumption was that in case of this interaction, we can say electron neutrino, I am taking this reaction, electron neutrino field is acting here, right? And we can say this electron neutrino field is analogous to the electromagnetic field, where we got emission of a photon from atomic nucleus, right? Or we can say from an atom, right? Gamma ray in case of nucleus, and ultraviolet or visible photon from the atom. So according to this theory, this emission of electron neutrino process from the nucleus is analogous to the emission of a photon from the atom or from the nucleus. So we can say here the electron neutrino field is analog to the electromagnetic field. And this electron neutrino field is very, very weak as compared to the strong force, right? That is acting inside the nucleus. So we call it as a weak force, right? So this was the fourth assumption, right? Fifth one. So there in these calculations we are using time dependent perturbation theory. Right. We have already gone through the time dependent and time independent perturbation theories in the quantum mechanics. Right. So because of the smallness of coupling constants, because of the weak force, we are using time dependent perturbation theory. Right. The next assumption was as the nucleons, right, are for example we can say neutron, proton or electron. Electron is although not a nucleon, but as electron is involved here, that's why I am saying that neutron, proton and electron, they are moving with very small velocity as compared to the velocity of light. So we are going to use here non-relativistic results of the physics or equations of the physics. We are using these results or equations of the physics, right? I mean, this is the non-relativistic treatment of this beta decay problem, right? So these were some assumptions that has been taken into account by the Fermi before developing a theory of a beta decay. Now I am going to write down the expression for the probability of emission of the electron that has momentum between PE and PE plus BPE, right? PE plus BPE. So for writing that probability, I am going to use a very, very important result of quantum mechanics, and that result is a Fermi-Golden rule. Fermi-Golden rule. According to Fermi-Golden rule, the transition probability, PPE means probability for the emission of electron that has momentum P to P plus BPE. That is given as 2 pi upon h cut into HIF square dn upon dE naught. This is Fermi-Golden rule. This is equation number 1. This is basically the Fermi-Golden rule. This Fermi-Golden rule, right, taken from the quantum mechanics, tell us the probability that an electron having momentum in the range of this PE to PE plus BPE, it is emitted per unit time, right? So this equation tell us this rate of the emission of electron having momentum between PE to PE plus BPE per unit time, and this is given by this equation. In this equation, this is Fermi-Golden rule. HIF, where HIF is the matrix element of interaction between initial and final state, right? And what is dn upon dE naught? dn upon dE naught, this is telling us about the number of quantum mechanical state, dn, number of quantum mechanical states available for the final system per unit energy interval, dE naught. So we can say it is representing the density of the final states, number of the allowed energy states per unit energy interval, right? Now we are going to find out these two values. First is HIF and then second is dn upon dE naught, and then we are going to put this value here in equation number 1, and then after we will get the expression for this probability, right? So the next part of this topic that will deals with calculating these two factors. So I am first of all I am coming to the first one, right? That is interaction matrix element. So as I told you that interaction matrix element, it is written as HIF, right? And according to the definition of quantum mechanics or equations of quantum mechanics, it is given as a wave function of the final state, right? The interaction Hamiltonian into psi initial wave function of the initial state and d tau, right? Here psi f and psi initial are the wave functions of the system in the final and initial state. H is the Hamiltonian operator that is describing this interaction between the initial and final state, and d tau is the volume element. Like this is equation number 2, right? Now let's consider the reaction for the conversion of, as I told you, a neutron into proton plus electron plus anti-neutrino, right? So I can even write this parent nucleus that gives you daughter nucleus plus electron plus neutrino, right? So in this case, the psi I, that is the wave function of the initial state, that will be the wave function of the parent nucleus. We can say the wave function of parent nucleus, right? And the psi final now, if I write down the psi final wave function of the final state, then it will be equal to the wave function of the daughter nucleus, right, multiplied by the wave function of electron multiplied by the wave function of anti-neutrino, associated with the electron. So I can say psi final is equal to psi final state, final daughter nucleus multiplied by psi electron multiplied by psi neutrino, right? So now I'm going to put all these values here, right? So I can say that HIF is equal to integration of, right? I'm taking Z here. I'm telling you what is the meaning of this Z. Psi final star. Psi final means bracket psi final star psi electron star psi neutrino. When you will take this was the wave function of anti-neutrino. So when you will take the star of this, it will become the wave function of neutrino, right? So this one, then into, it was a H Hamiltonian operator. So here I am writing M into psi initial d tau. Now here what is Z and what is M? M is a dimensionless matrix element which is describing this interaction, and it is an operator. We have actually replaced H with the M and Z, and Z is the coupling constant that is describing the strength of this coupling between the initial and final state. All these results have been taken from the quantum mechanics, right? So H is replaced by M operator and coupling constant. So I have written here, this is psi final star. Here star is not there because it is now representing the neutrino, otherwise it was anti-neutrino, and this is the initial, right? So as I told you that G is coupling constant, so I am writing down the value of Z here. It is according to Fermi, it is 0.9 into 10 raised to power minus 4 mega electron volt, right, Fermi meter cube. And it is analogous to the charge of electron, right, that is 1.6 into 10 raised to power minus 19 coulomb in case of electromagnetic interaction, right? So this is the coupling constant that determines the strength of this interaction between the initial and final state, and M is the matrix element, right, or operator we can say. So now I am writing down the wave functions, that is wave function of electron and wave function of neutrino, right? So we know very well from the knowledge of quantum mechanics that the wave function of electron, that will be written as a star, that will be written as a 1 upon under root b, right, exponential of minus iota upon h cut into p electron dot r. This is the wave function of the electron. Similarly, wave function of the neutrino. You can see here, neutrino associated with electron. I am writing this subscript. So the wave function of the neutrino, right, associated with electron, that will be again the same type, 1 upon under root b exponential of minus iota upon h cut, right, into p neutrino dot r. Here in these expressions, B is the volume of the system which encloses this entire reaction, right? And PE and P neutrino, these are the momentums of electron and a neutrino respectively. R is their position vectors. This is the expression for the wave functions. We have the knowledge of it from the quantum mechanics. Now I am going to put all these values here. So when we will put in this expression, like this is equation number 3, it was 2, so it is equation number 3. Then I am putting it in 3, I will get HIF is equal to Z into integration psi f star as it is 1 upon B. Well, I will multiply, because you can see here multiplication of these two, this factor is written as it is, multiplication of these two, 1 upon under root, 1 upon under root B, it will give me 1 upon B, right, into bracket exponential of minus iota upon h cut, right, into P electron plus P neutrino, right, dot R, this is bracket closes, right, and then after matrix element operator M, then psi initial and d tau. You can see here I have put all this value in this equation, right, M as it is, psi initial, d tau, and these two values are put here, right. Now then we simplify this exponential, right. We put the values of the electron momenta, neutrino momenta, which are usually of the order of mc, mass and the velocity of light. Then we found that this factor is nearly equal to 1 upon 50, right, exponential factor. So if I expand this exponential factor, we know very well it will expand according to the rule, that is exponential of minus iota upon h cut into PE plus P neutrino dot R, it will become 1 minus iota upon h cut into PE plus P neutrino dot R minus 1 upon 2 h cut square into PE plus P neutrino dot R, the whole factor square and plus so on. So I will get this. So as I told you that this factor is nearly equal to 1 upon 50. So when I will take the expansion, I can ignore all these values. I will only retain 1 here, right? So when I took this 1 and put it here, then after simplification, I will get HIF is equal to Z upon B integration psi final star, right, into M psi initial into D tau, right. So I can write it as Z upon V into MIF, right. This is the expression that I got. Here MIF represents this interaction, right. So now I simplified HIF, so I got HIF is equal to this factor, right. Z coupling constant upon volume in which this entire reaction is taking place, and MIF, right. Now this one thing is done that I was looking at for this equation, this one. Now I am going for a dN upon a dE naught, right. The second factor, that was dN upon dE naught. So as I told you that dN upon dE naught is representing the number of final quantum mechanics states available for the system per unit energy interval, right? So as far as dn is concerned, right, we have the knowledge of it from quantum statistics. You can recall Bose-Einstein and Fermi-Dirac statistics. So dn, we have calculated it there. It comes out to be 4 pi p square dp into volume B divided by the volume of one cell in a phase space, or we can say the volume of one energy state. In quantum mechanics, it is S cube, and this is the volume, total volume, available volume. So this is now giving me the total number of available quantum mechanical energy states. Once again, I am repeating that this factor has been taken from quantum statistics, Bose-Einstein or Fermi-Dirac statistics that you have already learned. The number of states is equal to total volume available in the phase space divided by the volume of one cell, energy cell, or one energy state, right? So dn is equal to 4 pi p square dp upon h cube. So if I write down its value for both electron and neutrino, then dn electron will be equal to 4 pi pe square dpe upon h cube. Similarly, dn for neutrino, it will also have the same value, 4 pi p neutrino square dp neutrino upon h cube, right? So when I want to write the total number of states, then I have to multiply it. So dn will become equal to 4 into 4, 16 pi square into I forget to write here b in both the cases, 4 pi p square into b. So 16 pi square b square upon h power 6, right? Then p e square p neutrino square d p e and d neutrino dp neutrino. So this is what I got for here, right? So this is what I got here, dn is equal to this. So I am going to the next page, right? Once again I am writing it here. I have to continue it from here. dn is equal to 16 pi square b square divided by h power 6 p e square p mu square dpe and dp mu, right? This was the expression. So if I divide this expression by de naught, then it is going to give me the number of energy states per unit energy interval. So dn upon de naught, that will give me 16 pi square b square divided by h power 6, right? Pe square p neutrino square dp neutrino electron dp neutrino divided by de naught. This is the expression that I got here. Let this is let's go to the previous page. It was equation number 3. So let this is equation number 4 and this is equation number 5, right? Now the total energy, as we have assumed in the beginning that it is E total energy, it is carried by the neutrino and electron, right? We have taken it in the beginning that the recoil nucleus do not carry any energy, right? Now if the electron energy is fixed, right, so in that case de naught will be equal to de neutrino. If we have the electron energy fixed constant, then in that case it will become this, right? We know very well that what is the relation between the momentum and energy for both electron and neutrino from the relation E square is equal to P square C square plus m naught square C power 4. So for electron it becomes E square is equal to P E square C square plus m naught square C power 4. This is for electron, right? And for neutrino, as the rest mass of the neutrino is 0, so we can say E neutrino square is equal to P neutrino square C square. So if I take the under root on both the sides, P, and I consider only the positive terms, E neutrino is equal to C into P neutrino. So here I can write P neutrino is equal to E neutrino upon C. Now E neutrino, from here you can see that E neutrino is equal to E naught minus E electron, right? So now I can write it, take it here. So it will get E minus E electron divided by C. So now I am going to put all these values here. First, let E neutrino is equal to C P neutrino. So if I take the differential of this equation, then it will give me D E neutrino is equal to C into D P neutrino, right? So now I am going to take all these values and going to put these values here in this equation number 5. So what I will get after putting these values, Dn upon dE naught, that is equal to 16 pi square B square upon h power 6 P E square, as it is. You can see here P mu square. Now P mu is equal to this factor, is equal to this one. So I am going to put it here, E naught minus E upon C and the whole factor square, right? This is whole factor square, right? Into, it was DPE, and then I have dP, neutrino divided by dE naught, dP neutrino divided by dE naught, dP neutrino upon dE naught. It is given here, right? Right. Now dE neutrino is equal to dE naught. You can see here dE neutrino is equal to dE naught. So I am putting it here. dE neutrino, it will become dE naught is equal to C into dP neutrino. So it is going to give me dP neutrino upon dE naught is equal to 1 upon C. So I am going to put here in this place, I am going to take it as 1 upon C. So you can take it here, 1 upon C now. One upon C. So when you multiply all these factors, what you got? You got dN upon dE naught is equal to 16 pi square B square h power 6 P electron square, right, into E naught minus E electron upon C, right, whole square dP electron upon C. This is what you got from here. Now putting all these values where, that this is equation number 6. Now equation number 6 and equation number this was, yes, 4. We are going to put the value of HIF and dN upon dE naught in this equation that I told you in the beginning, that is going to give me the value of PPE dNE. So you have to remember that the value of G upon V MIF there, right? So I am going to put all these values starting from 2 pi upon h cut. Once again I am writing this expression there. P probability of P E electron dPe, that is equal to 2 pi upon h cut into HIF square into dN upon dE naught. It was the equation. So I am putting these values, all these values here. So 2 pi upon h cut into HIF was G upon V square into MIF whole square into this factor 16 pi square B square upon H power 6 into PE square, right? You can take C square into C, it is C cube PE square into E naught minus E whole square dPe. This is equation number 7, right? Now this is the required expression that we were looking at, and this expression tells us about the probability of the emission of electron for a time that has momentum in this range, right? This was the equation that we were looking in the beginning according to Fermi golden rule. So we have calculated the value of HIF and dN upon dE naught, and from there we found this expression, right? So even this expression can be further written in a more modified form in this way, that is G square MIF square upon 2 pi cube C cube H power 7. I took this factor and this factor, then H power 7 now, right, into E naught minus EE whole square P electron square dPe. Equation number 8. Either equation number 7 or equation number 8, these two equations are enough to give us the value of this probability, right? So this is the expression we were looking at. This is the result of this Fermi theory of beta decay, right? So we have started from I'm going to the previous page. We have started from here with the assumptions of the Fermi theory that were made in the beginning, right? And then after assumptions we started from the Fermi golden rule. Then we calculated the value of HIF, that is the matrix Hamiltonian operator element of interaction, and then by calculating the value of HIF and dN upon dE naught, we put all these values in this expression, and then we arrived at this result, right, which is giving us the probability of emission of electron per unit time in the momentum interval of PE to dPe. Right? There was one mistake, I was looking at it. This was H cut was there. It was H cut power 7. So you can see all the factors. When you will take H cut as H upon 2 pi, then you can see you will again get this term. So you can do it, but both these equations are representing the same thing, right? So this is the expression for the probability of emission, right? So thank you very much.